In part one, we looked at growth decay models, and now we're going to look at some growth models. So let's say that we have this function that can be used to model population growth for human, insects, bacteria, whatever. And let's say we had 30,000 people in the year 2000 and 40,500 in the year 2010. And we're going to use this model to model the data. So our P sub 0 is kind of our starting point. So what's the value that we know of as a starting point? Well, that's this 30,000. Okay? So 30,000 e to the h t equals y. Now we also know this next value, that our population is at 40,500. How many years later? Well, 10 years later. So my time would be 10. So h times 10. So we're going to find h so that we have a specific model, and h would be considered kind of the growth rate, for lack of better terms. So we need to find h. So the first thing we're going to do is divide by 30,000, and I get 1.35 equals e to the 10h. Now this one's really easy to rewrite as a logarithm, right? Because it would be the natural log of 1.35 equals 10h. This is why we really like logarithms and base e. Then I would have to take natural log of 1.35. Then we're going to divide that by 10 and get 0.0300. So 0.03 would be approximately our h. So now we have our specific equation. P equals, or y equals, let's say y equals 30,000 e to the 0.03 t. So could we predict what the population would be in 2030? Yeah, that's 20 years after 2000. So you would just plug in 20 for your t. So y equals 30,000 e to the 0.03 times 20. And we'll get 54,660. I actually got 663.5. And I'd round that up to 64. Okay. The next growth model we're going to look at is an economics model. It's looking at a demand model. And so we have this demand model giving. And at what price per unit will the demand equal 40,000 units? So remember how this works. Q is the number of units or whatever, and it says Q is your thousand per thousand units. So we're going to be plugging Q in as 4,000 units. So the price for 4,000 units would be 30 times 3 to the negative Q divided by 2, so 4 divided by 2. And we end up getting approximately $3.33. How many units to the nearest 1,000 units will be demanded if the price is $17.32? So then we would just plug in $17.32 in for the price and solve for Q. So I divide by 30 first, and I get 0.577 equals 3 to the negative Q over 2. And that's, Q is kind of one of those fishy exponents because you get a little, it looks like a 9 sometimes. Natural log of 0.577 is going to equal, well, we're going to end up with the exponent coming in front times natural log of 3. So I'm going to take natural log of 0.577 divided by the natural log of 3 equals negative Q divided by 2. And I get 1.001. So Q is 1, but that doesn't mean just 1 unit. That's 1,000 units. The next one we're going to look at is what's called a Gompertz curve. It's a family of curves that that they use to describe human growth and development. But notice this is an exponent going to another exponent. So we have a rate going to the time. So it's a double exponent. And so to kind of see what happens is we end up with a plateau at the top. So a population increases, but it doesn't keep increasing forever. It kind of plateaus off. And so this model really depicts that well. So in this example, 100 represents the number of deer we started with. So this is deer on a small island. The growth rate is 0.03 and R is 0.2. And the time in this is representing decades. So let's see how we can work that. A hospital administrator predicts the growth in the number of hospital employees to follow a Gompertz. And I may be pronouncing that really wrong here. So what would be the number of employees when the facility opens? Well, that would be when time is 0, right? So if you plug in 0 for time, we're going to actually get 2,000, 0.6. And so I was mistaken on that other one about the deer. We should have done it right to the 0 power. So that ends up giving me a 1 here. And I end up actually with 1,200. So I apologize for the mistake on the deer one. We needed to plug in everything. So how many employees are predicted after 1 year? So what is T? T is the number of years. Okay, so 2,000 times 0.6 to the 0.5 to the 1. 2,000 parentheses 0.6 to the 0.5 to the 1 power. And we get 1,549.1. That's about 1,549 people. And if I look at the graph of this, now, I need to change some stuff, right? Clear that out. Turn off my plot. And we're going to type in the function in here. And let me go to a standard window and let's see if we see anything. That's not going to work too good. I already know that I start with 1,200 employees. This is not a good window. Talked about windows. So 0 to 10 years, that looks like it might be a good thing for the X's. But for Y's, I need to go well past, 1,500 or whatever. So let's go to like 2,500. That sounds like a reasonable number. Let's see if we see this pattern here. So it starts at 1,200 and then it's leveling off. And I wonder where it's leveling off yet. So it's going to level off at kind of a maximum value here. Up here it flattens out. So it says, what is the maximum value of n that the curve will approach? So I could hit trace and keep going. It's at 1989, 1998. What do you think it's approaching? 1999.5, 0.7. It's approaching 2,000. So that number in front really did mean something, and it actually means that that's our limit. So that's the limit of number of employees that hospital can take in. Okay, here's another example, and it's missing something, so I have a typo on this example. I will have to fix that. This should read n equals 100, parentheses 0.03 to the 0.2 to the t. So during what year will the deer population reach or exceed 70? So we want to know when it is at 70. Now this one takes a little while to do by hand. So I'm going to show you a couple of ways we can do this. I'm going to go into my y equals, and I'm going to put in that equation. And I'm also going to put in the line y equals 70. And I might need to adjust my window because these deer, they're not going to get much past 100. So I'm going to set this at like 120. So here's the graph. And I might need to zoom in a little bit more because it flattens out pretty fast. And there's a line at 70. Oh. Let's make this go from like -2 to 5. Let's see if that narrows it down any better. So here's the graph. That looks a lot better. And there's the line y equals 70. So I'm going to show what we're doing here. We can see this graph doing something like this. And what I did was I drew in the line y equals 70. And the reason I did that is because at this point right here, that would be the place where this graph equals 70. So I could go to second calc, intersect, enter, 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 and it's going to give me the exact intersection. And that's at t equals 1.42. And this was measured in decades. So if that's in decades, that means approximately 14 years. Now, so those curves describe situations in which growth is limited. There are other equations that model this phenomenon. We have these two ways of writing it. You won't have to know any of those. The second one is also called a logistic curve. That one, there is actually an option in the calculator to do a model using a logistic curve. But you won't have to write the equation. You're usually going to be given it. So we're given this one, and it's talking about computer tablets are being purchased more frequently than personal. It is one of the most frequently purchased. And the revenue from computer tablets is modeled by this function. So let's put it in the calculator. Clear out everything else. Alpha y equals gives us a fraction. Okay. I'm going to hit graph, but I know I'm kind of off on my graph because that's not going to be the best picture for it. Let's play with the window a little bit. Ooh, yeah, it's way down there. So this one doesn't have to be as tall. Let's try going back to like a 10 here. And maybe a 10 here. And seeing if that looks a little better. Oh, am I tall enough? I'm tall enough. Yay. Okay, so we have this graph, and it does this really cool thing. It goes swoop, and then it flattens off at the top. And it says use the function to estimate the sales revenue for 2020. So X is the number of years past 2014. So that would be when X is 6. So you could do it a lot of different ways. You could just plug in X. We're on the graph, so you could go to the table, or you could put trace 6. And it gives me the Y value that matches, which is 9.2336. And so that's approximately $9.234 million.